You lie in bed at night, staring at a ceiling you know is not really there, because above that plaster there is open space. Beyond the roof, the sky looks calm, almost gentle, a dark blanket with tiny lights punched through it. From the ground it feels like a backdrop, something painted, steady and safe. Yet every one of those lights is a witness to violence, to collisions, explosions and narrow escapes. Whole worlds have been melted, shattered and remade out there, while you sleep. The quiet you feel is an illusion. Tonight we are going to treat that peaceful sky like a crime scene and follow the clues it has been trying to show us all along. Astronomy is often described as looking up and admiring beauty, but in truth it is more like forensic work. We do not get to visit most of the places we talk about. We arrive late to the scene, after the main events are over. All we have are traces, bits of light, strange craters, leftover rubble, clouds of gas, little swings in the motion of stars. All of them tiny hints of something that happened long ago. Our job is to read those marks in the sky, the way a detective reads scuffs on a floor. If you step outside on a clear night, your eyes can pick out a few thousand stars at most. That already feels like a lot, but it is a tiny fraction of what is really there. Our galaxy holds hundreds of billions of stars. Beyond it, there are billions of other galaxies. Every point of light you see with your eyes is a bright tip of something much larger and more complicated. Many of those stars have their own planets. Some have belts of rubble. Some sit near clouds of dust that are still turning into new systems. You and I live in one small corner of this swarm. From down here on Earth, the solar system feels stable. The planets glide along predictable paths. The moon follows us through the sky. The sun rises on schedule. It is easy to imagine that things have always been like this, a clockwork that has been ticking in the same calm way for ages. The evidence refuses to support that picture. When we look closely at craters, at asteroid belts, at tilted planet orbits and odd moons, we see scars. The solar system we live in was not built gently. It was carved out of chaos. Even the earth under your feet remembers this. The ground may seem solid and safe, but buried inside rocks are hints of terrible impacts. Layers of ash, grains of glass that cooled in the aftermath of fireballs, sudden gaps in the fossil record, where entire families of creatures vanish. Our moon is covered in craters, each one the frozen record of a strike so violent that it melted rock. The calm, round face we see at night is actually a record of assault after assault. If you use the moon as a mirror, you are really looking at the danger our planet has faced. The first big clue that space is not gentle hides in something most of us ignore. Small streaks of light that flash overhead on random nights, shooting stars. We make wishes on them. We treat them like magic. They are actually tiny pieces of space rock burning up at high speed. Most are no larger than grains of sand, yet they slam into the top of our atmosphere faster than any bullet. Friction turns them into hot plasma. They leave a glowing trail for a second, then vanish. For every one you notice, many more skim in unseen. Larger pieces survive longer. Every so often something bigger comes in, a rock the size of a car or a house. The air roars in front of it. The object heats up and may explode in a powerful airburst that can shatter windows on the ground. Very rarely, a much larger one makes it all the way down and gouges a crater into the surface. On human timescales, those events are rare. On the timescale of Earth itself, they are expected and frequent. The planet has been bombarded for billions of years, and that bombardment helped shape everything we know. This is where the story starts to twist. The same impacts that can erase life also help create it. The rocks flying through space are not empty bullets. Many are full of useful minerals. Some carry frozen water. Some even hold organic molecules, the kind of carbon-rich chemistry from which life can grow. When those rocks hit a young planet, they deliver more than destruction. They also bring ingredients. Over millions of years, countless deliveries add up. It is like a dangerous rain that also fills the oceans. Our own world seems to have been built out of this rubble. The early solar system did not contain finished planets. It began as a cloud of gas and dust collapsing under its own gravity. In that cloud, tiny grains of rock and ice bumped into each other. At first, their collisions were gentle. They stuck together through static electricity and simple contact. Grain by grain, they became pebbles, then boulders. Eventually, those clumps grew so large that gravity itself started to help, pulling in more and more material. Astronomers believe that the first solid bodies to form in this disk of material were small worlds we now call planetesimals. Many of those early objects never had the chance to become full planets. They smashed into each other, they shattered. Fragments merged with other bodies, over and over, like an endless demolition derby. Rubble crashed and reassembled. Some of the survivors are what we see today as asteroids. They are not leftovers in the sense of being unimportant scraps. They are preserved samples of the building blocks that once tried to make worlds. When we send spacecraft to visit these small bodies, we are really sending probes into deep time. A rocky mountain floating in space may be only a few tens or hundreds of kilometers across, but it holds information from the first few million years of our solar system. Its composition tells us how hot or cold its birthplace was. Its craters reveal how often it has been hit since then. Some asteroids are solid chunks, others are loose piles of rubble, held together only by their own weak gravity. Each type records a different history of violence. From orbit, many of these objects look battered and desolate, but you can also see patterns, long ridges, smooth plains, frozen landslides sweeping down the flanks of ancient hills. They may be tiny compared to Earth, yet the same physics shapes them. A large asteroid has enough gravity that if you stood on it and threw a rock, that rock would arc back down to the surface. For you and me, that is a strange thought, a mountain in space that pulls back when you try to leave. The Moon offers an even clearer record. When astronauts looked down at its surface from orbit, they saw vast seas of hardened lava and bright rays of ejecta stretching out from fresh craters. There are almost no winds or rains there to erase those scars. Impacts that happened billions of years ago are still visible. That is what makes the Moon such a useful witness. It has been sitting next to us for almost the entire history of the solar system, quietly recording every big rock that came too close. On Earth, plate tectonics, erosion, and life itself erase old damage. Continents move, mountains rise and crumble, forests grow over craters, oceans open and close. Yet even here we find remnants. A ring of low hills that once marked the edge of a crater. A layer of shocked quartz, formed when rock was bruised by a shockwave that moved faster than sound. Thin streaks rich in rare metals that do not belong in normal crust. These are the fingerprints of ancient collisions, hiding in plain sight in the geology under our feet. One of the strangest clues is buried in a thin layer of rock that circles the planet, a boundary between older fossils and younger ones. Below that layer, the bones of dinosaurs are common. Above it, they are gone. The rock at that dividing line is rich in elements that are common in some types of asteroid, but rare in Earth's crust. It also shows signs of being laid down quickly, as if dust and debris rained from the sky after a single sudden event. Put together, it reads like the case file of a bad day for an entire world. When you add all these clues together, a pattern appears. Our solar system is not an untouched showroom. It is a place where things crash and break, where worlds are struck and sometimes erased. The planets we see today are the survivors of that long trial. Their smooth orbits are hard won, their moons are often the remnants of collisions. Even the gentle presence of our oceans may be the result of countless icy impacts that both scarred and watered the young Earth. So the peaceful night sky is an illusion in more than one way. It hides violence in time, stretching catastrophic events out over spans so long that no single human life can witness them. It also hides violence in distance. An impact that shatters a world on the far side of the galaxy would not rattle the glass in your window. You would never hear the explosion. All that reaches you is a faint change in light, arriving long after the fact. Space seems quiet because its loudest events are spread thin. If you could speed up time, the view would change. Stars would orbit the center of the galaxy like fireflies swirling around a drain. Clouds of gas would collapse into new suns. Planetary systems would flicker into existence and sometimes tear themselves apart. Asteroid belts would churn. Comets would dive inward on long-stretched orbits, graze a star, and swing back out. Over and over you would see violence and construction happening together. The universe would look less like a painting and more like a storm. Yet even at normal speed, you can still read the aftermath. You can look at a crater and ask what kind of object made it. You can measure the slight wobble of a star and infer that a planet is tugging on it. You can examine the spectrum of light from a distant galaxy and tell how fast it is moving away. Each of these measurements is a clue pulled from the dead light of old events. The more clues we gather, the clearer the hidden story becomes. That is the thrill of this kind of science. We are trying to explain a vast and violent history using only the softest of evidence. We rely on careful observation, on repeated checks, on instruments that can see what our eyes cannot. We argue, test, and refine. Over time, independent lines of proof start to agree. The same impact that leaves a crater in rock also leaves a chemical trace, and sometimes a layer of ash, and even a gap in the fossil record. When all those signs point in the same direction, we gain confidence that we are not just telling stories, we are uncovering real events. All of this might seem far away from your life. It is tempting to enjoy space facts as trivia, fun to hear, but easy to forget. The deeper truth is that this violent history built the stage on which your daily life plays out. The gravity that holds you to the ground is the same gravity that pulled dust into planetesimals and planets. The metals in your phone were forged in stars that died long before our sun was born. The water in your glass may include atoms that once floated inside a comet or an icy asteroid. When you lie in bed and listen to a story about the cosmos, you are not listening about an outside place. You are hearing the prequel to your own existence. Every collision, every flare, every slow drift of a planet in the early solar system helped decide whether a world like Earth could exist at all. Most star systems may never get that lucky balance. Some end in chaos, some freeze, some burn. The fact that you can relax under a roof and think about these things is itself a kind of cosmic miracle. So as we begin this long, slow exploration of space, keep that image in mind. The calm ceiling above you, the quiet sky beyond it, and behind that, a universe that has spent billions of years smashing and rebuilding itself. The tiny grains of rock that stuck together, the asteroids that formed and shattered, the planets that grew from the wreckage. Every simple point of light you see at night is the polished tip of a messy story. We are about to start reading those stories in detail, one clue at a time. When we started reading the scars on worlds, we were looking at the end of a long and messy story. To understand those scars properly, we need to rewind the tape, past the craters and shattered moons, all the way back to when there were no planets at all. Imagine the sun as a newborn, still wrapped in the leftovers of the cloud that made it. Around this young star is not a neat family of worlds, but a thick, rotating disk of gas and dust that stretches for billions of kilometers. That dust is not like household dust. It is a mix of tiny grains of rock, metal, and ice, smaller than smoke particles. Many formed in older stars that died and sprinkled their ashes into space. Some were cooked in violent shocks where gas clouds collided. Each little grain carries a history longer than any planet's lifetime. Now, in this swirling disk, they begin to collide. At first, the collisions are gentle. Grains drift into each other and stick thanks to small electric charges and surface forces. If you want a mental picture, think of snowflakes drifting down and landing on each other. One snowflake alone is fragile, but a pile of them can grow into a snowdrift. In the disk around a young star, the snow is dust and ice, and the drifting happens in slow motion. At these tiny scales, gravity is still too weak to do much. What matters is that the grains meet, cling, and refuse to separate. Over time they become fluffy clumps, more like dust bunnies than solid rocks. As these clumps grow, they begin to feel drag from the gas in the disk. The gas moves a little more slowly than the solid particles because gas feels a pressure gradient. The clumps lose energy and spiral inward, drifting toward the star. This creates a problem. If they drift inward too quickly, they fall into the star before they can grow big enough to resist. Planet formation has to solve this problem. Somehow, some regions of the disk must pile up enough material fast enough that gravity can take over before everything is lost. One idea is that turbulence in the gas creates pockets where dust collects, like eddies in a river where leaves gather. In these pockets, the concentration of solids gets high enough that the clumps begin to pull on each other gravitationally. Once that happens, growth speeds up. A loose cloud of small particles can collapse under its own gravity into a single, larger body. These larger seeds can sweep up nearby material more effectively. What began as a gentle drift of grains becomes a rush of growth. Soon you have objects the size of boulders, and then small mountains. Astronomers call them planetesimals. They are the first bodies big enough that their own gravity shapes them. If you were standing on one, you could jump and fall back down instead of drifting away. They orbit the star like all the other material, but each encounter between them is now a significant event. Two planetesimals that collide may shatter, or they may merge into a larger body. Which happens depends on how fast they meet and at what angle. This is where the violence enters the picture again. The early disk is crowded, orbits cross. Every planetesimal is surrounded by countless others moving at slightly different speeds and directions. Collisions are frequent. Some are slow and sticky, like bumper cars. Others are hyper-fast crashes that vaporize rock and spray molten droplets into space. Over millions of years, the statistics favor growth. On average, more mass ends up in larger survivors than in fine dust. Slowly, a few planetesimals in each region pull ahead of their neighbors. As these winners grow, their gravity starts to influence the orbits of bodies far away. They deflect smaller objects toward themselves. They stir up the random speeds of nearby rocks. This process, called runaway growth, turns a crowded field of many similar planetesimals into a small group of big protoplanets surrounded by leftovers. Each protoplanet is like a rough draft of a world, not yet smooth, not yet finished, but already massive enough to dominate its local space. In the region where Earth orbits today, these protoplanets may have been about the size of the Moon or Mars. Think of a dozen or more of them, sharing roughly similar orbits, weaving around each other in a slow, tense dance. Over tens of millions of years, their interactions grow more dramatic. Some collide and merge into larger bodies. Some are flung inward toward the star, or outward toward the cold edge of the system. Some may be ejected completely and wander through interstellar space as lonely rogue planets. The rocks that never quite made it into a planet become part of another important population. Between Mars and Jupiter lies a broad ring of objects we call the asteroid belt. It is easy to imagine it as the remains of a shattered world, but the evidence points in a different direction. It is more likely that this belt is a region where a true planet never finished forming. Jupiter's strong gravity stirred up the orbits of planetesimals there so much that gentle sticking collisions were rare. High-speed impacts broke bodies apart faster than they could grow. So the belt we see today is a frozen snapshot of a process that was interrupted. Its members are not all the same. Some are rich in metal, some are mostly rock, some contain a lot of water ice and carbon-rich material. When we look at them closely with telescopes and spacecraft, we see that many are not solid chunks but loose piles of rubble. They are made of fragments reassembled after countless collisions, held together by gravity and sometimes by a thin crust of fused material. Every time a mission has returned samples from one of these bodies, the story has become more detailed. Some grains are older than the solar system itself, formed in long dead stars. Some show signs of having been altered by liquid water, which hints that their parent body once had enough heat and internal complexity to sustain brief oceans. Others contain complex organic molecules, the raw chemicals needed for life. These are not simple rocks. They are time capsules, locked away in cold storage for billions of years. While this slow drama unfolds, the sun is also changing. In its earlier stages, it blows a powerful wind of charged particles that streams outward in all directions. That wind sweeps away much of the gas in the disk, especially the lighter elements near the star. As the gas thins, it becomes harder for small bodies to lose energy and spiral inward. The clock is ticking. Protoplanets that want to grow must do so before the gas vanishes. Otherwise, they will be left with only small rocky crumbs to feed on. Further out, past the region where water can stay frozen, the story changes. Here, grains of dust are cloaked in ice. Ice is sticky, so particles can grow larger more easily. The building blocks contain more volatile material like water and simple carbon compounds. This outer zone is where the cores of giant planets like Jupiter and Saturn likely formed. They grew fast enough to start pulling in gas directly, becoming massive worlds with thick envelopes. Their growth and later migration through the disk disturbed the orbits of many smaller bodies, flinging some inward and some outward. Some of the outward-flung objects ended up in distant reservoirs, like the Kuiper Belt and the even more remote Oort cloud. These distant swarms hold countless icy bodies that orbit the Sun on huge paths lasting millions of years. When gravity nudges one of them inward, it can appear in our sky as a comet. Comets, like asteroids, are leftovers from planet building. They are dirty snowballs that never became part of a world. When they heat up near the Sun, they release gas and dust, forming the glowing tails we see from Earth. The inward-flung objects, especially those rich in ice, played a critical role closer to the Sun. As they crossed the orbits of growing rocky planets, many collided with them. Each impact was both destructive and generous. Energy from the collision melted rock and sometimes vaporized entire regions, but it also delivered water and volatile elements. Over time, a steady rain of comets and water-rich asteroids may have given Earth much of its surface water. If so, our oceans are partly borrowed from the deep cold of the outer solar system. Meanwhile, the rocky protoplanets near the Sun continued their dangerous dance. The early history of Earth probably included multiple giant impacts. One of them stands out in simulations and in the chemical and physical evidence. A Mars-sized body is thought to have struck the young Earth in a glancing blow. The collision would have been beyond anything we can truly imagine, releasing enough energy to melt large parts of both worlds. Debris from that impact formed a disk around Earth, which later gathered into our moon. The details of that event are still debated, but the broad picture is supported by several lines of evidence. The moon's composition is similar to Earth's outer layers. Its orbit and angular momentum match what you would expect from a massive glancing impact. The lack of large iron in the moon compared to Earth's core fits the idea that most of the iron sank into Earth before the collision. In this view, our calm grey companion in the sky is literally made from the wreckage of a world-scale accident. For you and me, this has an odd emotional side. The moon that sets the rhythm of tides and lights our nights may also have been crucial in stabilising Earth's tilt and climate over long timescales. Without that giant impact, our planet might have spun and wobbled in a way that made long-term stable climates harder to maintain. If life needs long stretches of relative stability to grow complex, then our existence could be tied to that one chaotic collision. A destructive event created a tool for stability. It is worth pausing to notice how many times this pattern appears. Gentle processes and violent ones work together. Dust grains drift and settle, quietly sticking to each other. Then sudden impacts rearrange everything in an instant. Some bodies are shattered, others grow, and a few are thrown entirely out of the system. Over vast stretches of time, this mix of calm accumulation and sudden catastrophe builds a family of planets with different sizes, compositions, and histories. If you imagine trying to simulate this from scratch, you begin to appreciate the challenge scientists face. You would need to track billions of particles, then millions of larger fragments, then hundreds of protoplanets, each interacting with the star, the gas, and each other. Every slight change early on can lead to different outcomes. Yet when astronomers run these models with reasonable starting conditions, something striking happens. They often end up with a few inner rocky planets, a belt of leftovers, and some large outer planets. In other words, systems that look familiar. We can check these ideas against observations beyond our own neighbourhood. Telescopes that can see in infrared and radio wavelengths peer into star-forming regions where young stars are still wrapped in disks. In many of those disks, we see gaps and rings, places where material has been cleared out along certain orbits. One natural explanation is that growing planets have already begun carving paths through the dust and gas. In some cases, we may be watching newborn worlds vacuum up their surroundings in real time. Even more convincing are the planetary systems we have now discovered around other stars. Some look very different from ours, with giant planets hugging their stars on tight orbits. Others have several super-Earths packed close in, yet the basic themes repeat. There are small rocky bodies, larger, volatile, rich worlds, belts of debris, and signs of migration and scattering. These systems are not copies of the solar system, but they show that building planets from disks of gas and dust is a common outcome of star formation. All of this loops back to the small rocks we started with. When you hear the word asteroid, it might conjure a single grey boulder drifting in isolation. The deeper truth is that asteroids are fossilized steps in planet building. They are pieces of the process that never made it into a finished world. By studying their orbits, compositions, and structures, we are reading the rough notes left over from the solar system's early construction phase. Next time you see a picture of the asteroid belt as a tight crowd of rocks almost touching, remember that the real belt is mostly empty space. The rocks are far apart, and a spacecraft can fly through without much risk. But in the past, when there was more material and more crossing orbits, it was a heavier traffic zone. Many asteroids you could visit today are survivors of a time when collisions were more common and more energetic. They carry the bruises of that era on their surfaces. If you let your mind wander, you can place yourself inside that early disk. Imagine standing on a young protoplanet, feeling a weak gravity under your feet, watching the sky. Instead of a distant moon, you might see other protoplanets looming large, their surfaces mottled with fresh lava and glowing impacts. The stars themselves would be partly hidden by dust and gas. Every so often, a bright streak would mark a collision on the horizon. The night would feel less like a peaceful dome and more like the inside of a workshop. Thinking this way changes how you see the present. The stable orbits of today, the regular calendar of seasons and years, are not free gifts. They are the end result of countless trials, crashes, and rearrangements in the young solar system. Our planet is not a simple rock that appeared fully formed. It is a layered archive of events, each one built on top of the last, starting with microscopic dust caught in a collapsing cloud. Once you accept that dust can become mountains and rubble can become worlds, another question naturally appears. If this process is so universal, what kinds of strange planets has it built elsewhere, in disks that face different conditions from ours? What happens when the same rules of gravity and collision play out closer to a star, or around a heavier sun, or in a disk with more heavy elements? The answers are written into the exoplanets we see scattered across the galaxy, waiting for us to read them. Those answers began to arrive only recently, when we learned how to spot planets around other stars. For most of human history, the only worlds we knew were the ones in our own sky. The inner rocky planets, the gas giants, the belts of rubble. We took that layout as normal. When astronomers first detected planets circling distant suns, they expected to see familiar families. Instead, the universe handed us misfits. Worlds that seemed to break every rule our own solar system had taught us. The first confirmed planet around a normal star was nothing like the textbook picture of a distant Jupiter. It was a giant world about the mass of Jupiter, yet it whipped around its star in just a few Earth days. Instead of drifting slowly far from its sun, it hugged close, so close that its year was shorter than your work week. Its atmosphere was baked by intense light. Its clouds, if it had any, would have been scorched and stretched by tidal forces. Astronomers gave this new kind of world a name: Hot Jupiter. Finding that first hot Jupiter felt like walking into a familiar room and discovering the furniture bolted to the ceiling. It challenged assumptions that had seemed almost obvious. In our solar system, the giant planets live far out where ice is stable and gas is plentiful. Closer in, Where the sun's heat is stronger, we see only smaller, rocky bodies. So how did a giant, gas-rich world end up right next to its star? Something about the way planets move and interact after they form had to be different and more dramatic than we had imagined. To make sense of this, it helps to understand how we find such planets in the first place. You cannot simply take a picture of most exoplanets. They are too faint and too close to the overwhelming glare of their stars. Instead, we look for the way a planet's gravity tugs on its star. As a planet orbits, it pulls the star slightly toward and away from us. That motion changes the colour of the star's light in a regular pattern. This method, called the radial velocity technique, is sensitive to heavy planets on tight orbits, which is exactly why hot Jupiters were some of the first we saw. Another powerful method watches for tiny dips in a star's brightness when a planet passes in front of it. Imagine a moth flying across a street lamp. The lamp looks slightly dimmer for a moment as the moth blocks a small part of the light. In the same way, if a planet crosses the face of its star from our perspective, the starlight drops by a tiny amount on a regular schedule. Sensitive telescopes can measure these dips and use them to infer the planet's size and orbit. The Kepler Space Telescope used this transit method to discover thousands of planets. Because these techniques are biased towards certain types of planets, they showed us an exaggerated view at first. Heavy bodies close to their stars are easier to find than small ones far away. Even with that in mind, the variety we saw was surprising. We found worlds bigger than Earth but smaller than Neptune, which we call super-Earths and mini-Neptunes. Our own solar system has nothing in that size range. We found planets in orbits so tight that they complete a lap in less than a single Earth day. We found systems with several large planets packed closer to their star than Mercury is to the Sun. Try to picture a hot Jupiter up close. A giant planet orbiting so near its star that its atmosphere screams under the heat. The day side glows at temperatures that can melt many metals. Winds race around the planet at thousands of kilometers per hour, trying to even out the heat between day and night. The planet is likely tidally locked, showing the same face to its star, just as the moon shows us only one side. On the permanent day side, the sky would blaze with unending sunrise. On the night side, heat would bleed through the air and perhaps through rivers of plasma clouds. Now imagine a super-Earth, a planet 2 or 3 times the size of our world, with several times the mass. Gravity there would be much stronger. Each step would feel like walking while someone presses down on your shoulders. Mountains might be shorter, because rock yields more easily under the higher weight. If the planet has a thick atmosphere, the air pressure at the surface could be crushing. Depending on its composition, such a planet might be an ocean world with deep global seas, or a rocky furnace with a hot, dense blanket of gas. Some of the most extreme super-Earths discovered so far are ultra-hot lava worlds. Their orbits skim so close to their stars that the surface rock melts into oceans of magma. On the star-facing side, the ground would glow like molten metal in a foundry. Vaporized rock might rise into the air, condense on the cooler night side, and fall as mineral rain. It is an environment beyond any natural place on Earth, yet it follows the same rules of physics: gravity, heat, radiation and chemistry, playing their usual game in a more intense arena. It is easy to treat these worlds as curiosities, but each one is a data point in a larger story. They show us that the simple picture we built from our home system is just one outcome among many. When disks of gas and dust fall around young stars, the details matter. How much material is there? What is the exact temperature profile? How quickly do planets grow? How strongly do they interact and migrate? Slight differences in these starting conditions can lead to very different families of planets. Migration is one of the key ideas that helps explain the weird systems we see. A planet does not have to stay where it forms. As it interacts with the gas in the disk and with other planets, it can slowly spiral inward or outward. A giant world that formed far from its star may gradually move inward as it trades energy and angular momentum with the surrounding material. If nothing stops this drift, the planet can end up on a tight, hot orbit. In some systems, giant planets plough through the inner disk, scattering smaller bodies and leaving behind a very different arrangement from our own. We also find planets in places that would look unstable to us. Some circle around both members of a close pair of stars, tracing wide paths around a double sun. Others orbit one star in a wide binary, with a second star shining in the background sky. The light on such worlds would be strange. Seasons could be complex, driven not only by the tilt of the planet's axis, but also by the changing positions of two suns. Imagine standing on the surface and watching twin sunsets, or seeing one sun eclipse the other on a regular schedule. Perhaps the most haunting class of worlds belongs to stars that are small and dim compared to our Sun. Red dwarf stars are common in the galaxy. Their light is cooler and more reddish, and their habitable zones sit much closer in. Planets in those zones are likely tidally locked, with one side always baking under the small sun and the other side frozen in darkness. Yet in the twilight belt between day and night, there could be regions with moderate temperatures. Astronomers call that region the terminator. If life can adapt to such extremes, it might find a home in those narrow rings of eternal dawn or sunset. So far we have talked mostly about planets that still circle a star. There is another, more lonely category: rogue planets. These are worlds that drift through space without any parent star at all. They are not bound to a solar system. They wander the galaxy, lit only by faint starlight from far away and by their own internal heat. How do such orphans form? In many simulations of planetary systems, some bodies are kicked hard enough during violent interactions that they escape entirely. They are slung out like marbles flicked off a table. Evidence for rogue planets comes from a method called gravitational microlensing. When a massive object passes in front of a more distant star, its gravity bends and briefly magnifies the star's light. If the lensing object is a free-floating planet, the brightening is short and subtle. Surveys have seen events that match the signatures of planetary mass bodies without visible stars attached. The numbers are uncertain, but it is possible that there are as many or more rogue planets in the galaxy as there are bound ones. What would it be like to stand on such a world? There would be no sunrise or sunset, only a black sky littered with distant stars and perhaps the faint ribbon of the galaxy. The only steady energy source would be the heat left over from the planet's formation and from any radioactive elements in its interior. If the world has a thick atmosphere rich in insulating gases, that internal warmth could keep the surface above the freezing point of some liquids, even in the darkness. Oceans of exotic fluids might exist under heavy skies. Life, if it arises, would have to adapt to a sunless environment, perhaps feeding on chemical gradients instead of light. Between planets and stars lies another group of objects that blur the categories: brown dwarfs. They are too small to sustain long-term hydrogen fusion in their cores, which is the process that makes normal stars shine steadily. Yet they are often much larger than any planet, many times the mass of Jupiter. They form more like stars, through the direct collapse of gas, rather than through the slow sticking of solids. Some brown dwarfs have planets of their own, creating miniature systems in the dark. Their surfaces, if we can call them that, are deep layers of gas lit by fading heat. Brown dwarfs remind us that our labels are conveniences, not laws. We like to draw sharp lines: planet, brown dwarf, star. In reality, nature gives us a spectrum. An object with 13 times the mass of Jupiter can start burning a heavier form of hydrogen for a while. Slightly lighter bodies cannot. Do we define a planet by mass? By how it formed? By whether it orbits a star? Each choice gives a slightly different catalogue. The universe itself continues unconcerned, building objects all along the scale, wherever the conditions allow. As we keep collecting exoplanet data, patterns begin to emerge. One surprising result is that small planets seem to be more common than giant ones. Many stars host multiple worlds a bit larger than Earth, with short orbital periods of only a few days or weeks. If you lived on one of those planets, the changing positions of neighbouring worlds in the sky could be visible even to the naked eye. They would swing back and forth much more quickly than our bright planets do. Nights would be full of moving points, each one a nearby world. All these discoveries invite a quiet, unsettling question. Is our solar system normal? In some ways, yes. We have inner rocky planets, outer giants, and leftover belts. In other ways, we look odd. We have no hot Jupiter, no super-Earths packed close to the Sun. Our giant planets sit at moderate distances and have relatively calm orbits. That combination may be rare. It might be one of the reasons our planet has enjoyed a long period without catastrophic disruptions to its orbit or rotation. You can think of our system as one outcome in a cosmic lottery. The rules are set by physics, but the exact result depends on many small variations. Slightly more mass in the disk, a slightly different migration path for Jupiter, a single extra giant collision, and we might have ended up with a very different layout. Maybe a super-Earth where Mercury is now. Maybe a hot Jupiter sweeping away inner rocky worlds. Maybe an Earth that was kicked into a wild, stretched orbit that swings between deep freeze and intense heat. When you hear about strange exoplanets, it is tempting to treat them as distant oddities that exist only in diagrams and artist impressions. Yet each one is as real as our own world, with weather, geology, and perhaps even chemistry that runs for billions of years. Somewhere out there, storms rage in atmospheres thicker than any on Earth. Lava flows across continents of glowing rock. Winds howl through narrow twilight zones between light and dark. Seas slosh on worlds that never see a sunrise. If you let these images settle in your mind, they change the way you look at our quiet sky. The points of light you see are not just stars. Many are entire planetary systems, each with its own crowded sky, its own calendar of seasons and catastrophes. We are no longer limited to imagining a single type of world. Instead, we are confronted with a zoo whose members are more varied than early dreamers ever guessed. This richness is not a distraction, it is a clue. It tells us that planet formation is robust and flexible, capable of building almost any environment allowed by gravity and matter. In that context, Earth becomes even more special. Not in a mystical sense, but in a statistical one. We live on a medium-sized rocky planet, at a moderate distance from a stable star, in a system without close orbiting giants that would shake everything apart. Our orbit is nearly circular. Our axial tilt is not extreme. For billions of years, these quiet conditions have given life time to arise, adapt, and complexify. This does not mean we are the only habitable world. It does mean our path here has threaded a narrow channel through chaos. As we continue our investigation of the cosmos, this contrast will keep tugging at us. On one hand, the rules are universal. Gravity behaves the same way in every system. On the other hand, the outcomes are wildly diverse. That tension between order and variety, between familiar physics and alien landscapes, is one of the central themes of modern astronomy. It pushes us to ask a new, deeper question. If planets and stars can create so many environments, what does that mean for the lives of the stars themselves, the engines that make all these worlds possible? When you saw how many strange planets exist, you were really seeing the work of their stars. Every world orbits a power source. Every orbit is a life spent in the glow of a particular kind of furnace. The shape and fate of that furnace is set almost entirely by one simple thing: how much mass it has. Once you know a star's mass, you can start to predict its childhood, its calm middle age, and the way it will die. Stars are born in great dark clouds of gas and dust. From far away, those clouds look quiet, but inside them, gravity is always whispering. In some regions, the gas becomes slightly denser than average. That extra weight pulls in even more material. A small knot forms, then tightens again. As the cloud fragment shrinks, it heats up. At first, the warmth comes just from gravity turning falling motion into heat. If you could fly inside one of these forming stars, you would not see a neat sphere of light. You would see a churning ball of gas, hotter toward the center, cooler at the edges, still wrapped in some of the dust from the original cloud. This is the protostar phase. The new star is not yet truly shining, but it is already pushing back with light and wind, trying to clear a cavity around itself. Deep in the center, the temperature and pressure continue to climb. At a certain point, The conditions cross a threshold. Hydrogen atoms, the simplest building blocks in the universe, are squeezed so hard and heated so much that their nuclei can merge. When that happens, mass is converted into energy. The core lights up with nuclear fusion. The star has taken a crucial step. It has turned on. From this moment, two great forces battle inside the star. Gravity wants to pull everything inward. Fusion in the core wants to push everything outward. As long as those two influences balance, the star can live a long, steady life. It will shine at a more or less constant brightness, slow converting hydrogen into helium in its core. This quiet stage is what astronomers call the main sequence. On the main sequence, mass is destiny. A small star sips its hydrogen slowly. It shines dimly and can last far longer than the current age of the universe. A star like our Sun burns brighter, uses its fuel faster, and has a lifetime of roughly 10 billion years. Very massive stars blaze with fierce light and heat. They tear through their fuel in only a few million years. Ironically, the more massive a star is, the shorter its life. Our Sun is in its stable middle age. It has been shining for about 4.5 billion years. It will keep doing so for roughly that long again. Even now, it is not a calm place. Its surface seethes with boiling gas. Loops of charged particles arc high above the surface. Dark spots mark areas of intense magnetic activity. Occasionally, great flares burst outward, sending waves of particles and radiation rushing through the solar system. From Earth, we see only a steady disk of light. We feel warmth on our skin, we see blue sky by day, and we forget that this piece is built on balance. The core of the Sun is a place of crushing pressure and blistering temperature. Photons created there take many thousands of years to random walk their way out through the crowded interior. By the time they reach the surface as visible light, the events that gave birth to them are ancient history. Imagine being able to speed up the Sun's life, to watch its entire career play out in a single human day. You would see its brightness gently increase as the core fills with helium, and the balance between gravity and fusion slowly shifts. The star would seem calm, but inside it is always changing. Hydrogen is steadily turned into helium ash. The core gradually contracts to keep fusion going. Eventually, in every star like the Sun, the hydrogen in the very centre runs low. Fusion in that central region falters. Gravity begins to win, and the core starts to shrink. As it does, fresh hydrogen in a shell around the core gets compressed and heated. Fusion lights up in that shell. The outer layers of the star feel the extra energy and respond by expanding. The star swells. From the outside, such a star transforms into a red giant. Its surface cools as it balloons outward, so its colour shifts toward orange and red. The radius can grow so large that, in the case of our Sun, it may engulf Mercury and Venus, and possibly reach near the orbit of Earth. The inner planets will face searing heat, rocky surfaces will melt, atmospheres and oceans, if any remain, will be stripped away. Inside the red giant, the core continues to contract. It is now mostly helium. As it shrinks, it heats further. When the core reaches the right combination of temperature and pressure, helium fusion can begin. Helium nuclei merge to form heavier elements like carbon and oxygen. This new burning phase adds another layer of complexity to the star's structure. You now have a hot core of helium burning, surrounded by a shell of hydrogen burning, wrapped in huge, bloated outer layers. This stage is unstable. The star can pulse and shed mass. Strong stellar winds carry material away into space. The outer layers thin. Eventually, in a star roughly the mass of the Sun, those outer layers drift off completely. They form a glowing shell of gas around the remaining core. Ultraviolet light from the hot, exposed core makes the gas shine in delicate colours. We call these shells planetary nebulae, even though they have nothing to do with planets. Through a telescope, they look like round, ghostly bubbles. The exposed core itself is now a compact object called a white dwarf. It is about the size of Earth, yet it contains a large fraction of the star's original mass. Its matter is packed extremely tightly. A teaspoon of white dwarf material would weigh as much as a mountain. There is no fusion in its interior now. It shines because it is still very hot, and it will slowly cool and fade over billions of years, like an ember left over from a long finished fire. This is the fate of stars similar to the Sun. They live long, swell into giants, shed their outer layers, and end as dense, cooling cinders. The story is different and more dramatic for very massive stars. If a star starts out with many times the mass of the Sun, its core reaches much higher temperatures. It can fuse not only hydrogen into helium, but also helium into carbon, carbon into heavier elements, and so on, climbing the ladder of the periodic table. In the core of such a massive star, fusion begins to happen in shells. Hydrogen burns in a shell around a helium-burning core. Later, helium burns in a shell around a carbon-burning core. The structure becomes layered, like an onion. Each inner shell burns hotter and faster than the one outside it. The outer layers of the star may look calm, but beneath them, energy flows through many stacked zones of nuclear fire. The more advanced the fusion, the shorter the timescale. A massive star might spend millions of years in the hydrogen burning phase, but only thousands in helium burning. The stages that create elements like neon, magnesium, and silicon can last only years or even days. The star is rushing through its fuel supplies, building heavier and heavier elements in its center. All the while, gravity is waiting for the moment when the core can no longer push back. There is a hard limit in this climb. Fusing light elements into heavier ones releases energy. It allows the star to support its own weight. But when the core's composition approaches iron, the rules change. Fusing iron into heavier elements does not release net energy. It costs energy instead. Once too much iron builds up in the core, fusion can no longer generate enough outward pressure to balance gravity. The core becomes unstable. At that point, events move with terrifying speed. The iron core collapses inward. Electrons are crushed into protons. Densities spike to levels far beyond anything ordinary matter can withstand. The core shrinks from something the size of Earth to something more like a city in a fraction of a second. The outer layers of the star feel this sudden loss of support and begin to fall inward too, slamming into the rebounding core. When that infalling matter strikes the compressed core, a shockwave forms. Neutrinos, ghostly particles produced in huge numbers in the collapsing core, stream outward and help push the shock. In a successful core collapse, the shockwave rips through the star's outer layers and blows them apart into space. From the outside, we see a supernova. For a brief time, the dying star can outshine an entire galaxy. A supernova is one of the most energetic events the universe produces. It hurls heavy elements into space at tremendous speeds. The shockwave plows into the surrounding gas, heating it and compressing it, sometimes triggering new rounds of star formation. The expanding debris shell glows in many wavelengths of light. When we look at remnants like the Crab Nebula or others, we are seeing the ashes of one star seeding the next generation. In that blast, something profound happens. Elements forged in the core and shells of the star are mixed into the wider galaxy. Carbon, oxygen, silicon, calcium, and many others are created or spread this way. Some of the iron that ends up in your blood, the calcium in your bones, the silicon in your computer chips, all were built in stars that ended in similar, violent deaths. When people say we are made of star stuff, they are not being poetic. They are describing a literal chain of events. Not every stellar death looks like a classic bright supernova. Some massive stars may collapse more quietly, funneling much of their mass directly into a black hole. Some lose large amounts of material in strong winds before they explode. Some die in tight binary systems where mass transfer changes their evolution. There is an entire family of explosions called thermonuclear supernovae that occur when white dwarfs in binary systems reach a critical mass and undergo runaway fusion. Those events also spread heavy elements and serve as useful distance markers across the cosmos. If this sounds like a confusing catalogue, remember the core pattern. Stars are born from collapsing clouds. They shine by fusing lighter elements into heavier ones. The more massive they are, the hotter and shorter their lives. When fusion can no longer support the core, gravity takes charge. The result is either a gentle settling into a white dwarf state or a violent collapse and explosion that leaves behind something even stranger. One way to bring this closer to your life is to think in terms of recycling. The gas cloud that formed our sun was not pure hydrogen and helium. It contained traces of heavier elements created in earlier generations of stars. Those earlier stars lived, shone, and died, enriching the interstellar medium. Some died gently, some in enormous blasts. Their remnants drifted, mixed, and eventually became part of the cloud that collapsed to form our system. That means the atoms in your body have been inside stars before. Some were fused in long-lived suns similar to ours. Others were forged in the brief blaze of massive stars and hurled out in explosions. Long before any planet existed, those atoms sat in hot, ionized gas, then cooled into dust, then were drawn into a new star-forming region. Over billions of years, the same basic material has been used and reused, assembled into different structures, dissolved, and reformed. If you go out on a dark night and look up, you are seeing stars in many stages of this cycle. Some are still in their main sequence quiet period. Others are red giants nearing the end of steady life. In distant galaxies, you can sometimes catch the sudden flare of a supernova. Even when you cannot see the details, the statistics tell us that in the time you spend watching, somewhere in the universe, several massive stars will have died spectacularly. Our own part of the galaxy carries scars of past explosions. In the constellations we teach to children, there are regions where expanding shells of gas glow faintly in radio and X-ray light. Inside some of those shells sits a compact remnant, spinning or collapsing, warping space or emitting pulses. These remnants are not just curiosities. They are the direct outcomes of the processes we have been following. They represent the next chapter in our forensic investigation. Before we move to those remnants, it is worth holding one more picture: the night sky as a graveyard. Not in a gloomy sense, but in a factual one. Many of the points of light you see are middle-aged stars. Some are near the ends of their lives. A few already have corpses nearby, dense objects left behind by earlier deaths. The galaxy is full of these unseen relics. They bend light, tug on nearby stars, and sometimes rip matter from companions, lighting up again in bursts. We now know that stars do not simply fade and vanish. They leave behind strange, condensed states of matter. Some are so dense that a spoonful would outweigh a mountain. Some spin hundreds of times per second. Some trap light completely. These objects are not obvious from casual stargazing. You only find them by listening to subtle signals or watching how they disturb their surroundings. Yet once you know they exist, it becomes impossible to look at any bright star without wondering what kind of corpse it will someday leave. Understanding those stellar corpses is the next step if we want a complete picture of the universe as a crime scene. We have seen how the victims lived, how they burned their fuel, and how they went out. Now we need to follow what remains, the compact hearts left behind by violent deaths, and ask how they continue to shape the space around them long after the explosion fades from view. The corpses of stars are nothing like the bodies they came from. A massive blue giant dies and leaves behind something no bigger than a city. A gentle yellow sun ends as an object the size of Earth, but with the mass of a star. For the first time in our story, the actors are smaller than the worlds that orbit them, yet their influence can be enormous and sometimes terrifying. If normal stars are the lamps of the universe, these remnants are its hidden power tools. Start with the quietest of the three, the white dwarf. When a star like the Sun finishes fusing its core hydrogen and helium, sheds its outer layers, and reveals its hot heart, that heart compresses into a white dwarf. It is about as wide as Earth, but packs in roughly half the mass of the Sun. Matter in a white dwarf is crammed so tightly that atoms have been squeezed into a rigid sea of electrons and nuclei. Quantum rules, not chemical bonds, are now what keeps the object from collapsing further. If you could somehow scoop up a spoonful of white dwarf material, it would weigh tons. The surface gravity would be hundreds of thousands of times stronger than Earth's. Drop a pebble from a meter above that surface, and it would hit at a significant fraction of the speed of light. Yet from a distance, a solitary white dwarf is easy to miss. It shines with a hot white or blue light at first, then slowly cools over billions of years. It is a fading coal in the dark. White dwarfs become much less quiet when they live in close pairs. In a tight binary system, a white dwarf can steal matter from a normal companion star. Gas spirals in, heats up, and sometimes detonates in bursts on the surface. We see those bursts as flashes of high-energy light. In more extreme cases, if the white dwarf gains too much mass, the entire star can undergo a runaway fusion reaction and explode in a thermonuclear supernova. That blast rips the white dwarf apart and adds more heavy elements to the galaxy. Even so, white dwarfs are still the mildest of stellar corpses. The next level up is a neutron star. These form when a massive star dies in a core collapse supernova. In that event, the core contracts past the white dwarf stage. Pressures become so intense that electrons and protons merge into neutrons. The matter becomes a degenerate neutron fluid. The collapse halts only when the neutrons themselves push back through quantum forces. The result is an object roughly 20 kilometers across, with more mass than the Sun. Imagine a city-sized sphere that weighs more than a star. A teaspoon of neutron star material would weigh billions of tons. The surface gravity is so fierce that falling just a few centimeters would release more energy than a nuclear weapon. We say these numbers easily, but they describe conditions far beyond anything humans will ever touch directly. Neutron stars spin. They inherit their parent star's rotation and speed it up as they collapse, like an ice skater pulling in their arms. Some newborn neutron stars spin dozens or even hundreds of times per second. They also carry intense magnetic fields. Those fields, twisted and amplified by the collapse, channel charged particles into beams that shoot out from the magnetic poles. When one of those beams sweeps across Earth, we see a pulse of radio or X-ray light. The pulses arrive with astonishing regularity. Some are more precise than the best atomic clocks we have ever built. We call these objects pulsars. To a radio telescope, a pulsar is a lighthouse in the sky, blinking on and off as its beam spins past us. Each pulse is produced by a city-sized sphere of ultra-dense matter spinning in the dark. The first pulsars puzzled their discoverers so much that they briefly wondered whether they might be messages from other civilizations. The signals were that regular. Later observations showed that pulsars are natural. Even so, their behavior lets us test physics in regimes we cannot reproduce on Earth. By watching how pulsars slow down, glitch, or wobble, we can probe the strength of their fields and the structure of their interiors. Some neutron stars take the magnetic field game even further. These are magnetars. Their magnetic fields are so strong that they can distort electron orbitals and affect the vacuum itself. When the crust of a magnetar shifts or cracks, the field can rearrange violently and release enormous bursts of high-energy radiation. We see those as sudden flares. A single flare from a magnetar thousands of light years away can briefly outshine all the other stars in its host galaxy in gamma rays. Neutron stars often have companions. In a close binary, a neutron star can pull gas from a normal star. The stolen material forms a hot disk around the neutron star and eventually crashes onto its surface. That impact releases X-rays. Telescopes tuned to that energy range see these systems as bright, variable X-ray sources. By measuring their patterns, we can estimate the masses of the neutron stars and confirm that they really are as dense and compact as our theories predict. So white dwarfs and neutron stars compress matter to extraordinary densities and create extreme conditions. Yet in both cases, there is still a surface. You could, in theory, point to a radius where matter ends and vacuum begins, even if you could never stand there. Black holes are different. They are what happens when collapse goes past any stage where pressure can fight back. Gravity wins completely. The result is a region of space-time from which nothing can escape. A black hole forms when a core heavier than a few solar masses collapses beyond the neutron star limit. The matter that falls inward crosses a boundary called the event horizon. Once inside, it can no longer send signals to the outside universe. Light itself, which normally sets the speed limit for everything, cannot climb out of that gravity well. From far away, it looks as though infalling matter slows and fades as it approaches the horizon. In its own frame, it crosses in a finite time, never to return. We cannot look inside a black hole. The laws of physics as we understand them now cannot fully describe the singularity at the centre, the point where density becomes formally infinite. But we can work with what we see from outside. Black holes can have three properties that matter to the outside universe: mass, spin, and electric charge. In practice, astrophysical black holes are mostly described by mass and spin. Despite their name, black holes are not empty. Space around them can be full of hot gas, magnetic fields, and radiation. When a black hole feeds, matter falling in forms a disk. Friction in that disk heats the gas to incredible temperatures. It glows brightly in X-rays and other high-energy light. In some systems, magnetic fields channel part of the inflowing material into narrow jets that blast outward along the poles at nearly the speed of light. Those jets can stretch across thousands of light years. We first suspected black holes from their gravitational effects. A visible star orbiting an unseen massive companion. A tight cluster of hot gas moving too fast to be bound by anything else. By applying Newton's and Einstein's laws to those motions, astronomers inferred the presence of compact objects with masses far above any neutron star. Over time, multiple independent lines of observation strengthened the case. Watching accretion disks, measuring X-ray bursts, tracking stellar orbits near galactic centers. At the heart of our own galaxy sits such a monster. In the direction of the constellation Sagittarius, radio telescopes see a bright, compact source called Sagittarius A star. By tracking how nearby stars move around this invisible point, astronomers have measured a central mass of about 4 million suns, packed into a region smaller than our solar system. That is the signature of a supermassive black hole. If you could ride along with one of the stars that orbit close to this central mass, you would see the gravitational field swing you around at thousands of kilometers per second. One star, called S2, follows a long, stretched path that carries it close to the black hole every 16 years. During its nearest pass, it moves fast enough that relativity has to be included to explain its motion. Its orbit, mapped over decades, has become one of the best tests of Einstein's theory in a strong field. Black holes reveal themselves in other ways too. In recent years, detectors have picked up ripples in space-time that pass through Earth from distant cosmic collisions. These are gravitational waves, predicted by Einstein and confirmed by instruments like LIGO and Virgo. The events we see often match the signature of black holes spiraling together and merging. Two compact objects dance around each other, radiate gravitational energy, and finally coalesce into a single, larger whole. The final burst of waves carries information about the masses and spins of the participants. Listening to these waves feels like eavesdropping on the universe's most violent private moments. We are hearing, not seeing, pairs of massive bodies collide in otherwise dark corners of space. Each detection adds to our census of black holes. It tells us how often such mergers happen and what kind of masses are common. We discover black holes dozens of times the mass of the Sun, far heavier than those found in many X-ray binaries. All this might sound far away, but black holes are not exotic in the sense of being rare. They are expected outcomes of stellar evolution for the heaviest stars. Given the number of massive stars that have ever lived, the Milky Way alone should contain millions of stellar mass black holes drifting through its disk. We see only a fraction, those that actively feed or that merge. The rest are dark, anonymous pits of gravity, interacting only through their pull on nearby matter. The extreme nature of black holes also raises deep theoretical puzzles. One of them concerns information. In normal physics, information about a system is never truly destroyed. It can be scrambled and spread out, but in principle, it remains. Black holes challenge this rule. If matter carrying detailed information about its structure falls in, and if only a few simple properties survive outside, where did the information go? Hawking radiation, a quantum process that lets black holes slowly evaporate, complicates this story. Reconciling all these ideas has become one of the central questions at the edge of physics. For our purposes, we can set that puzzle down gently and step back to the bigger picture. From a human vantage point, black holes and neutron stars are the universe's ultimate heavy machinery. They stir gas in galaxies, power jets that can regulate star formation, and recycle energy and matter on large scales. The deaths of massive stars that create them also sow heavy elements into space. These compact objects are both tombstones and engines. When a star in a galaxy pulls matter into a central supermassive black hole and lights up as an active nucleus, the radiation and jets from that process can heat and push gas out of star-forming regions. That feedback can slow the birth of new stars. Over cosmic time, such episodes help shape the growth of galaxies themselves. So the behavior of these invisible cores is tied directly to the large-scale structure we see when we photograph deep fields of the sky. Once you know that, images of galaxies change. A calm spiral with a bright center is no longer just a pretty swirl of stars. It is a city of hundreds of billions of suns, revolving around a central mass that might be millions or billions of times heavier than our own star. In the halo of that galaxy drift leftover stellar corpses, white dwarfs cooling in silence, neutron stars flickering in radio and X-rays, black holes drifting like unseen sinkholes in the gravitational field. Think back to the idea of the night sky as a crime scene. We have followed the evidence from tiny dust grains all the way to planets, stars, and now the densest remnants of stellar death. Each step revealed a new layer of structure and a new kind of violence. Yet all of this has taken place on relatively small scales, inside galaxies, or in the cores of stars. The universe has a larger pattern we have not yet examined. If you pull the camera back far enough, you stop seeing individual stars at all. You see galaxies as points of light. You see them arranged not randomly, but in filaments, sheets, and clusters, leaving empty voids between. That pattern is not decoration. It is a fossil of the way matter moved and clumped in the early universe. To understand why galaxies are where they are and why their shapes differ, we have to climb another rung on the ladder and read the sky at the largest scales we can imagine. When you zoom out far enough, individual stars disappear. Even whole clusters blur together. The universe turns into a mist of faint smudges. Those smudges are galaxies. Islands of hundreds of billions of stars, gas clouds, and dark invisible mass, all held together by gravity. At first glance, they seem sprinkled randomly. But when we map their positions carefully, a pattern emerges that is anything but random. Imagine a three-dimensional spiderweb stretched across space. The threads are made of galaxies. Where the threads cross, the knots are clusters. In between lie huge empty regions called voids, vast volumes with very few galaxies at all. Astronomers call this pattern the cosmic web. It is the large-scale skeleton of the universe. Understanding how that skeleton formed is another step in reading the night sky as evidence. We build this picture by taking deep surveys of the sky. Telescopes scan large regions, measuring the positions and distances of hundreds of thousands of galaxies. Plot those points in 3 dimensions, and you see filaments, walls, and bubbles. It looks almost biological, like a network of nerves or blood vessels. Yet it is made not of cells, but of stars and dark matter, spread over hundreds of millions of light years. The central question is why matter arranged itself this way. If the early universe began in a hot, dense state and then expanded, you might expect it to smooth out over time, like gas spreading evenly in a room. Instead, we see clumps and chains. The answer lies in small differences that were present from the beginning. Tiny variations in density, no larger than 1 part in many thousands, gave gravity something to work with. In regions that started slightly denser than average, gravity pulled matter in a little faster. Those regions grew more massive, which increased their gravitational pull, which attracted even more matter. A slow runaway began. Over billions of years, these overdense regions grew into the filaments and nodes we see today. Underdense regions lost matter to their neighbours and became voids. The cosmic web is the grown-up version of those tiny first ripples. We know those initial ripples were real because we can still see their frozen imprint in the sky as a faint afterglow. The whole universe is filled with a background of microwave light, left over from a time when it was hot and opaque. Tiny variations in the temperature of that background map the early density differences. When we compare those maps with modern galaxy surveys, the match is striking. The same kinds of patterns appear, just stretched and evolved. Look at a single rich cluster, one of the bright knots in the web. It can contain thousands of galaxies bound together by a shared gravitational field. Most of the visible galaxies are spirals and ellipticals, swarming like bees around an invisible centre. Between them lies hot gas that glows in X-rays. When we measure the motions of the galaxies and the pressure of the gas, we find something surprising. There is not enough visible matter to account for the depth of the cluster's gravity well. This mismatch is one of the strongest clues that most of the mass in a cluster is dark. Not dark in the sense of shadowed, but dark in the sense of not interacting with light at all. Whatever this dark matter is, it reacts almost only through gravity. It does not shine, absorb, or reflect. It forms a kind of invisible scaffold. Galaxies and gas settle into its potential wells like leaves gathering in the hollows of a landscape we cannot see directly. We can map this hidden shape by watching how clusters bend light. Light passing near a massive object does not travel in a straight line. Space itself curbs, and the path of the light curbs with it. When a cluster sits between us and more distant galaxies, its mass acts like a lens. It magnifies and distorts the images of background objects. By measuring those distortions, we can infer the distribution of mass, both visible and dark, in the lens. These gravitational lensing maps show large halos of dark matter enveloping clusters and extending beyond their visible edges. They also reveal filaments between clusters, wispy bridges of mass where few bright galaxies live. In effect, lensing lets us feel the weight of the cosmic web with our instruments. It confirms that the bright parts we see are only a thin skin wrapped around a much larger, invisible structure. Within that structure, galaxies are not passive. They move, collide, and merge along the threads of the web. Small galaxies fall into larger ones. Clusters grow by eating smaller groups. When galaxies interact, their stars generally pass by each other without colliding, because stars are tiny compared to the distances between them, but their gas clouds can crash and compress. Those collisions can trigger bursts of new star formation, lighting up regions that were previously quiet. If you have ever seen an image of two galaxies in the middle of a collision, with long tidal tails stretching out from them, you have seen this process in action. Gravity pulls stars out into arcs and streams. Gas clouds ram together and ignite. Supermassive black holes at the centres may be fed with new material, flaring as they swallow gas. Over time, the two systems settle into a single remnant, often an elliptical galaxy with little cold gas left. On the vast scale of clusters, similar dramas play out. Entire clusters can collide. The dark matter halos pass through each other almost unchanged. The galaxies inside behave mostly like test particles, moving along with the halos. The hot gas, though, slams together, heats further, and slows. In one famous system, called the bullet cluster, this mismatch between the gas and the gravitational mass provides a clear, visual separation between normal and dark matter. Think of clusters and filaments as the largest traffic flows in the universe. Matter streams along them, drawn by gravity toward nodes. In the densest nodes, conditions are ripe for active galactic nuclei. These are galaxies whose central black holes are feeding aggressively. Gas falls inward, heats up, and shines brightly. Sometimes jets blast outward from the centre and push on the surrounding gas, stirring and heating it. This feedback can regulate how much new star formation happens in the host galaxy. So the lives of galaxies, the growth of black holes, the rate at which stars are born, and the structure of the cosmic web are all linked. The universe is not a static backdrop with galaxies scattered on it. It is an evolving network. Gravity gathers material, gas cools and forms stars. Those stars live, explode, and return energy and heavier elements to the gas. Black holes feed and blow winds. The cycle continues, gradually changing the balance between hot and cold gas, between bright young stars and older, redder populations. When we look at a map of the cosmic web, we are seeing that network in a particular era. Over time, the pattern does not remain fixed. Filaments grow thicker as more matter flows along them. Clusters become heavier and more tightly bound. Voids expand as they lose mass to their surroundings. On the largest scales, the web becomes more pronounced, even as the overall expansion of space drives galaxies farther apart. The expansion itself adds another layer of complexity. On short scales, gravity pulls things together. On very long scales, between distant clusters, space is stretching. The rate of that stretching appears to be accelerating, driven by something we call dark energy. We know it is there because distant supernovae and other measurements show that galaxies are receding from each other faster than simple models would predict. Yet we do not know what dark energy actually is. You can think of dark energy as a property of space that makes it want to expand more rapidly. As the universe grows, dark energy's influence does not thin out like normal matter. Instead, it stays roughly constant per unit volume. That means that in the far future, as matter gets more spread out and gravity's pull weakens, dark energy will dominate. The cosmic web will not vanish, but growth will slow. Distant clusters will slip out of contact with each other as space between them expands too quickly for gravity to overcome. From your vantage point on Earth, all of this is hidden behind familiar constellations. The Big Dipper, Orion, the Southern Cross. These lines we draw in the sky connect stars that are at very different distances and that belong to different branches of the web. When you trace the shape of a constellation, you are unconsciously tracing part of a much larger pattern that stretches far beyond what your eyes can see unaided. Modern surveys turn those simple pictures into three-dimensional atlases. They give us catalogues of positions, motions, and distances. You can fly virtually through those datasets, steering through clusters and threads, diving into voids. In those journeys, you start to sense the scale difference between the systems we have already discussed and the cosmic web itself. A galaxy becomes a dot. A cluster becomes a small knot. Our entire local group of galaxies shrinks to a speck in one filament among many. Yet even on these scales, you can still see echoes of smaller processes. Galaxies in dense clusters tend to be older and redder, with less star formation, perhaps quenched by repeated interactions and harsh environments. Galaxies in quieter filaments, or near the edges of voids, may have more gas and more active star birth. Environment matters. Where a galaxy sits in the web helps decide what kind of life it leads. This brings the investigation full circle. We began with the night sky over your bed, wondering why it looks so calm. We peeled back layers of evidence and found that planets formed through collisions, stars lived and died through nuclear fusion and gravity, and their corpses shaped their surroundings. Now we see that all of those events happen inside a larger structure, formed by the slow amplification of tiny initial ripples. The universe on the largest scales is less like a cloud of dust and more like a living network. Knowing this, you might ask a very natural question. If the universe has a skeleton, when did the bones first start to form? How early did the first filaments appear? How long did it take for the first stars and galaxies to light up the web? To answer that, we have to use one more crucial fact about light itself. When we look far away, we also look back in time. When you look far away, you are not seeing those objects as they are right now. You are seeing them as they were when their light began its journey. Light moves very fast, but not infinitely fast. It takes time to cross space. The farther away something is, the longer that light has been travelling. In a very real sense, the night sky is a time machine that works through your eyes. The moon is a little more than 1 second in the past. The sun is about 8 minutes behind the present. The bright stars you know from constellations can be years or centuries out of date. Distant galaxies are millions or even billions of years behind the time on your clock. When you look up, you are not seeing a single moment frozen onto the dome of the sky. You are seeing a layered history, stacked by distance. This is not just a poetic idea. It is the key that lets us reconstruct the story of the universe. If we can measure how far away an object is and how fast it is moving, we can place it on a timeline. We can watch galaxies at different distances and see how they change as we look further back. That is how we learn that the universe is not static, it is expanding. The more distant a galaxy is, the faster it seems to recede. That relation between distance and apparent speed, discovered by Edwin Hubble and others, is one of the cornerstone clues. It tells us that space itself is stretching. Imagine dots painted on a balloon as it inflates. Each dot moves away from the others as the rubber stretches. No single dot is the center. In a similar way, every galaxy sees other distant galaxies receding, not because they are flying through space like bullets, but because the space between them is growing. If you play that expansion movie backward in your mind, you get a universe that was once much denser and hotter. Not just stars packed together, but everything compressed. Galaxies, gas, radiation, and dark matter all squeezed into a much smaller volume. As you go back further, the temperature rises. At some point, it becomes so high that atoms cannot hold onto their electrons. The universe turns into a glowing fog of charged particles and light. In that early hot fog, light could not travel far without being scattered. Photons bounced off electrons again and again, like beams of light trying to move through the center of a thick cloud. The universe was bright but opaque. There were no stars yet, no galaxies, only a nearly uniform soup with tiny variations in density. Those tiny variations are the seeds of the cosmic web we see today. As the universe expanded, it cooled. After a few 100,000 years, the temperature dropped enough for electrons and protons to combine into neutral atoms. With fewer free charges to scatter off, light suddenly could travel much farther. The fog cleared. The universe became transparent. The glow that filled space at that moment did not vanish. It has been streaming through the cosmos ever since, stretched to longer and longer wavelengths by the ongoing expansion. Today, we see that ancient glow as the cosmic microwave background. It bathes all of space in a very faint, nearly uniform radio-like light. When scientists first detected it by accident with a radio antenna, they did not know what it was. Later work showed that its spectrum matched what you would expect from a hot, dense, early universe that has cooled over billions of years. It is a fossil light, the oldest direct picture we have. The microwave background is not perfectly smooth. Careful maps reveal tiny temperature variations, parts that are slightly warmer or cooler than average. Those small differences match the pattern of early density ripple. Regions that were a little denser show up as slightly cooler spots because gravity affected how light climbed out of them. In those maps, you are seeing the universe as an infant, only a few 100,000 years old. Imagine holding two images side by side in your mind. One is a map of the cosmic web today, with filaments and clusters spread over billions of light years. The other is the mottled pattern of the microwave background, with flecks of slightly different temperature. The correspondence is not exact point by point, but the statistics match. The web grew from those flecks. The same small ripples that you see in that ancient glow became the large structures where galaxies now live. If we look slightly later in time, we are still ahead of the first stars. The universe after the fog cleared was filled with neutral hydrogen and helium, slowly cooling, still almost dark. There were no bright sources yet, only the dwindling relic glow. This period is sometimes called the Cosmic Dark Ages. It did not last forever. Gravity was still at work, pulling matter into the slightly denser regions. Over tens and hundreds of millions of years, clouds grew and collapsed. Inside those collapsing clouds, the first stars ignited. They were likely very massive compared to typical stars today. Massive stars are hot and bright and short-lived. They poured out intense ultraviolet light. That radiation began to break apart the neutral hydrogen around them, stripping electrons away again. Slowly, bubble by bubble, the universe was reionized. It changed from a fog of neutral atoms into a more transparent medium with large regions of ionized gas. We see hints of this transformation when we study the light from very distant quasars and galaxies. Their spectra carry the marks of hydrogen between us and them. At certain distances, the absorption pattern changes, suggesting that the fraction of neutral gas was higher in the earlier universe. By gathering many such observations, astronomers can piece together a timeline of when the first luminous objects switched on and how quickly they transformed their surroundings. Telescopes like Hubble and newer ones like the James Webb Space Telescope push this work further. They can detect very faint, very distant galaxies whose light has been stretched into the infrared by expansion. These galaxies are so far away that we see them as they were just a few 100 million years after the beginning. Often they look small and irregular, like tiny clumps. They are likely members of the first generations of galaxy building. When you see an image of one of those early galaxies, pause for a moment. You are looking at a place that existed when the universe was less than a tenth of its current age. You are seeing stars that burned and died long before our sun formed. Their light spent billions of years crossing space to reach the mirror of a telescope, and then the sensor that recorded it. It then travelled through cables and computers until it arrived, in some indirect way, in your eyes. Stepping back even further in time, beyond the Dark Ages, brings you to the first few minutes after everything began. In that early phase, the entire observable universe was smaller than a galaxy is today, and much hotter. Temperatures were so high that normal atoms could not exist. Protons, neutrons, electrons, and radiation all occupied the same dense, blazing environment. Nuclear reactions happened everywhere, not just in the cores of stars. During those first minutes, a brief but critical process unfolded. Protons and neutrons combined into the lightest nuclei. Hydrogen, which is just a single proton, dominated. A quarter or so of the mass became helium nuclei. Small traces of deuterium and lithium also formed. Heavier elements did not appear in significant amounts then, because the conditions changed too quickly. The universe expanded and cooled, shutting down those fusion reactions. The predicted mix of these light elements is one of the classic tests of the hot, early universe model. When we measure the abundances of hydrogen, helium, and deuterium in very old gas clouds, they match the values expected from those first few minutes of nuclear burning. That agreement is like finding the same fingerprint at multiple crime scenes. It gives us confidence that we are telling the right large-scale story. Everything heavier than that initial helium mix had to be built later, in stars. That means the universe began as a very simple chemical place. Mostly hydrogen, some helium, almost nothing more. Over billions of years, cycles of star formation, stellar death, and gas recycling enriched that mix. Each generation added more carbon, oxygen, iron, and other elements to the interstellar medium. By the time our sun formed, the gas it drew from was already seasoned by many earlier lives. Now connect that back to the light that hits your eyes at night. Each photon is not just a particle of light, it is a messenger from a specific time and place. Light from a nearby star may have started its journey in the recent history of our galaxy. Light from a very distant galaxy may have left when the universe was still assembling its first major structures. Light from the cosmic microwave background comes from a time when no stars had yet formed, only a glowing plasma. As you listen, you can imagine the sky as a layered shell of these messages. Closest are local signals, flares from our sun and neighbouring stars. A bit farther out are the photons from ordinary galaxies in the modern cosmic web. Beyond them are the dim smudges of early galaxies, stretched into red and infrared. Furthest of all is the ancient background glow, a nearly uniform sea of microwave light that has been travelling for more than 13 billion years. The fact that we can see this far back is almost unsettling. It means that on clear nights, without leaving your pillow, you are in optical contact with a huge fraction of the universe's history. You cannot resolve the details with your unaided eyes, but the photons are there, passing through, bathing your body, filtered by the atmosphere. You are not an outsider staring at a distant story. You live inside the volume that has been changing since those first minutes. There is another quiet question hidden here. If we are surrounded by so many stars and galaxies, why is the night sky dark? You might think that in an infinite, eternal universe filled uniformly with stars, every line of sight would eventually end on a bright surface. the sky would glow as bright as a stellar photosphere. It clearly does not. The darkness between stars is one more piece of evidence that the universe has a finite age, and that light from very distant regions has not had infinite time to pile up. This puzzle, sometimes called the dark sky paradox, connects directly to the expanding universe picture. Because space has been stretching, and because there was a time before stars existed, there are limits to how much light can reach us. The expansion also redshifts light, pushing much of the background into wavelengths your eyes cannot see. What remains visible as starlight is a thin frosting of brilliance on top of a much larger, invisible story. If you could change your eyes to see in microwaves, the night sky would no longer look dark. It would glow gently in every direction with the afterglow of the hot, early universe. If you could see in infrared with great sensitivity, you would see the faint whispers of very distant galaxies filling what now looks like empty space. Different parts of the spectrum reveal different chapters of the same saga. This way of looking, combining distance, wavelength and time, is what turns astronomy into a forensic science. We cannot rewind time, but we can look at many distances and piece together how things changed. We can compare young galaxies with mature ones, see how star formation rates evolve, and track how the chemical mix of the cosmos grows richer. We can trace how the cosmic web thickened and how the microwave background patterns connect to present structure. All of this brings us to a deeper level of curiosity. It is one thing to know that the universe had a hot, dense beginning and has been expanding and cooling ever since. It is another to ask why the expansion looks the way it does now. Measurements tell us that something beyond ordinary matter and radiation is shaping the large-scale motion of space itself. A form of energy that does not clump, that acts more like a property of the vacuum than like a gas. As you lie there listening, you can feel the narrative reaching a kind of hinge. We have followed how light lets us see back in time, how tiny ripples grew into the web, how stars and galaxies lit up the darkness. The next natural question is not only where everything came from, but where it is going. What unseen forces are steering the future of the cosmos, and what kind of night sky will distant beings see when most of today's galaxies have faded from view? When you wonder about the future of the night sky, you are really wondering about a balance of forces. One of them you already know well: gravity. It pulls mass together, builds planets, shapes stars, sculpts galaxies, and ties clusters into the cosmic web. The other force is stranger. It does not pull things together, it pushes space itself to expand faster. It shows up not as a tug, but as a quiet acceleration written into the universe. We only stumbled on this second influence quite recently. For decades, astronomers assumed that the expansion of the universe should be slowing down. Gravity, from all the matter in space, ought to be putting on the brakes. The big question was whether that braking would be strong enough to stop the expansion and reverse it, or only slow it without ever halting it. To test this, teams of observers turned to special stellar explosions, thermonuclear supernovae that always reach roughly the same peak brightness. Because their intrinsic brightness is similar, they can act as standard candles. By comparing how bright they look to how bright they ought to be, we can estimate their distances. By measuring how much their host galaxies are redshifted, we can find how fast those galaxies are receding. When the results came back, they did not match the simple picture. Distant supernovae were dimmer than expected. That meant they were farther away than they should have been if the expansion had been slowing at a steady rate. The best explanation was unsettling. The expansion had started to speed up. Instead of coasting under gravity, the universe had begun accelerating. To describe this, cosmologists introduced a term you have now heard many times: dark energy. It is not a new kind of light. It is a name for whatever is causing space to expand faster. The word dark here means unknown, not evil. Dark energy does not behave like normal matter or normal radiation. It does not clump into galaxies or filaments. It seems to be a property of space itself. One simple model treats dark energy as a constant energy density that fills all of space. As space expands, there is more of it, so the total dark energy increases. Its gravity is repulsive in the sense that it drives expansion rather than resisting it. At early times, when the universe was dense and matter was packed close together, normal gravity dominated. As expansion spread matter out, dark energy became more important. Today, it appears to be the main driver on the largest scales. If you picture the history of the universe as a race between gravity and expansion, the opening era belonged to gravity. Small ripples grew into clouds, galaxies, and clusters. The middle era, including the current age, is a transitional time. Gravity still shapes structure on smaller scales. Dark energy governs the very long-range behavior, setting how quickly distant galaxies slip away from each other. In the far future, dark energy will win more and more decisively. Galaxies in our local group are bound together strongly enough that they will stay near us. The Milky Way and Andromeda are already on a collision course. They will merge into a single larger galaxy over billions of years, but more distant galaxies will not share that fate. Once they drift beyond a certain distance, the accelerated expansion will carry them away faster than their light can ever reach us. That means that for observers living far in the future, the cosmic web will appear to thin out. Clusters that are visible to us now will fade beyond their horizon. Their light will be redshifted to wavelengths too long and too faint to detect. The night sky from a future Earth-like planet could show only a single merged galaxy floating in blackness, with no clear evidence of an expanding universe beyond. It is a strange thought. Much of the evidence we use today to infer the big picture, like the pattern of distant galaxies and the microwave background glow, will gradually become inaccessible to future astronomers. For them, reconstructing the true history of the cosmos could be much harder. In that sense, you and I live at a privileged time. The sky above us still carries most of the clues we need to read the full story. Dark energy might not be constant. Some models imagine that its strength could change over time. If it grows stronger, expansion could speed up more dramatically. In extreme scenarios, the acceleration could eventually overwhelm all gravitational bonds, tearing clusters, galaxies, and even solar systems apart. This idea is sometimes called the Big Rip. It is a speculative edge case, not the current best fit, but it shows how sensitive the future is to the exact behavior of this unseen component. On the other side, if dark energy slowly decays, its influence could lessen in the deep future. Gravity could then regain some ground. The universe would still be very expanded and thin. Structure growth would be sluggish, but the story would tilt a little more back toward clumping. Right now, the data suggest a nearly constant dark energy, but our measurements have limits. We are still learning how precisely we can pin its behavior down. Whatever fine details turn out to be true, most scenarios share one broad feature. The universe will keep expanding. Matter will get more spread out. New star formation will gradually slow as the available cold gas is used up or heated. Galaxies will age. Their bright blue young stars will give way to older, redder populations. Over fantastically long timescales, the cosmic stage will grow dimmer. On the scale of a human life, even of all human history, this future is unimaginably remote. Stars like our Sun live for billions of years. Red dwarfs, the small, efficient stars, can shine for trillions of years. That is 1,000 times the current age of the universe. As long as those small stars burn, there will be points of light in the darkness. Planets can still orbit them. Chemistry can still happen in their warm zones. After those long-lived stars finally exhaust their fuel, the universe enters another phase. Stellar remnants dominate. White dwarfs slowly radiate away their stored heat and cool into black dwarfs. Neutron stars and black holes continue to orbit within whatever structure remains. Occasionally, through rare interactions, compact objects might merge, giving off short bursts of gravitational waves and light. But overall, the cosmos will grow quiet. Even then, processes continue. Over extreme timescales, orbits change through interactions and gravitational encounters. Some stars and remnants are flung out of galaxies, others sink toward the center. Black holes can merge and grow. Eventually, on timescales so long that normal language hardly suffices, even the largest black holes will begin to lose mass through Hawking radiation, a slow quantum effect that lets them evaporate. As those black holes shrink, they will emit a faint drizzle of particles. In the final moments of their lives, they will release a brief flare of energy, and then vanish. After that, if dark energy remains, space will be largely empty. A handful of low-energy photons and light particles will drift in an ever colder, thinner vacuum. This is sometimes called the heat death or big freeze, not because the universe becomes literally cold in every sense, but because there are no remaining free energy gradients to power complex structures. That is one class of possible endings. There are others, though current evidence makes them less likely. One is a big crunch, where expansion eventually halts and reverses, leading to a final collapse. Another is a big bounce, where collapse triggers a new expansion. Yet another involves phase changes in the vacuum itself, in which the underlying rules of physics might change abruptly. These ideas are still speculative. They sit at the edge of what current observations can constrain. From your bed under the night sky, this might all feel very abstract. You are dealing with daily tasks, personal worries, and local joys. Why should it matter what happens to stars trillions of years from now? One answer is that these stories give context. They place your existence on a timeline that stretches from the first few minutes after everything began to a very distant, quiet future. They show that you live in the brief era when stars are still plentiful and the night is still meaningfully bright. There is also a more immediate point. The same physics that governs the fate of the universe also governs the stability of your local environment. Gravity that shapes galaxies also shapes the orbit of Earth. Nuclear reactions that power stars are the same kind of processes we harness carefully in reactors and less carefully in weapons. Understanding these forces is not just a philosophical exercise. It is a way of knowing what keeps your world possible and what can threaten it. Dark matter and dark energy, though mysterious, have already influenced your life. Dark matter helped gather the gas that formed the Milky Way. Without its extra gravity, our galaxy would be smaller and less massive. The timing of star and planet formation would shift. Dark energy set the pace of expansion. Its value affects how quickly structure grew and how dense the universe was at key moments. If those numbers were very different, the cosmic web might not have developed in a way that allowed long-lived stars like the Sun to form. So when you hear that most of the universe is made of invisible components, you are not hearing about a distant curiosity. You are hearing about parts of reality that quietly shaped the room you are in. Your atoms come from stars. Your planet orbits in a galaxy held together by dark matter. That galaxy swims in an expanding space steered by dark energy. You are woven into all of these layers at once, even while you deal with ordinary human days. There is one more subtle question that often arises when people think about these grand timescales. If the universe is headed toward a long dimming, does that make everything meaningless? Does the fact that galaxies will someday fade erase the value of what you do now? Physics itself cannot answer that. What it can offer is a different framing. The rarity of your moment does not reduce its worth, it enhances it. You live in a window of cosmic time when the night sky is rich with information, when you can see both nearby stars and distant galaxies. When the microwave background is still detectable. When the big clues about the origin and fate of everything are, in principle, all around you. That means your species, if it chooses, can understand its situation in a way that future species might not be able to. Imagine a far future civilization living in a single merged galaxy, with no visible cosmic web and no detectable background glow. They might conclude that their galaxy is the entire universe. Their cosmology could look like ours did before we discovered expansion. For you, that veil has been lifted. You can know, with reasonable confidence, how your atoms were forged, how your star was born, and how the larger environment will likely evolve. Seen this way, the eerie long-term future of the universe is not a threat hanging over the present. It is a backdrop, a reminder that conditions change, and that complex patterns, like life and consciousness, bloom in certain eras and not in others. That makes the present not trivial, but precious. A short, bright interval in which matter has arranged itself into eyes and minds that can look back and ask questions. As you listen, you might feel a quiet weight in that realization. It is one thing to know that stars will die. It is another to know that awareness itself may be a temporary feature of the universe, arising when the balance between gravity, radiation, and chemistry is just right. This does not tell you what to value, but it does underline that your ability to value anything is part of a chain that began in nuclear reactions and cloud collapses billions of years ago. We have followed that chain outward, from your pillow, to the roof, to the sky, to the galaxies and beyond. We have watched planets form from dust, stars live and die, remnants shape space, and invisible components steer the expansion of everything. The last step is to turn back inward and ask what all of this means for the small, warm world where you actually live, and for the fragile species that has only recently learned to read the sky at all. All of this might sound grand and distant, but it has always been about here, about this one small planet where you are lying right now, about the air you draw into your lungs and the atoms that make your bones. The universe is not something you watch from outside. You are inside the story, built from its earlier chapters. Follow a single atom in your body back through time. Perhaps it is a carbon atom in a cell in your heart. Long before you existed, long before Earth was a planet, that atom did not yet exist. Its ingredients were simpler particles drifting in a young galaxy that had only just begun to form stars. Those particles were swept into a massive cloud of gas. Gravity compressed that cloud until the center grew hot enough to ignite fusion. In that star's core, lighter nuclei fused into heavier ones. After millions of years, through layers of nuclear reactions, carbon emerged as one link in a chain of creation. When that star died, it did not do so quietly. It threw its outer layers back into space, enriched with freshly made elements. That material mixed with surrounding gas, cooling into dust grains and thin clouds. Over and over, clouds like that fell inward, formed new stars, and seeded their surroundings with more heavy elements. Eventually, part of that enriched gas became the cloud that formed our sun. The same collapse that lit our star also flattened into a disk where planets would grow. The carbon atom that would one day sit in your heart rode inside that disk as part of a tiny grain. It stuck to other grains, became part of a rock, and then part of a larger body in the early solar system. Perhaps it was locked up for ages inside an asteroid. Perhaps it spent time in a comet, frozen in the deep cold far from the sun. Collisions and gravitational nudges shuffled it around. At some point, that body struck the growing Earth, or released dust that rained down into the atmosphere. The atom became part of the crust, or the oceans, or the air. On Earth, chemistry took over where stellar physics left off. In warm pools, deep ocean vents, or other hospitable niches, simple molecules linked together. They copied themselves, varied, and sometimes broke. Out of countless trials, some arrangements of atoms proved better at surviving and copying. Over immense time, those tiny improvements stacked into the complex machinery we now call life. Your carbon atom moved into that living cycle. It joined molecules that formed early cells. Later it might have been part of a plant, catching sunlight and carbon dioxide. Then it was eaten, digested, and woven into animal tissue. Generation after generation, it was passed along, sometimes buried, sometimes released, sometimes caught again in new chains. At some point in all that, it joined a molecule in your own body. That molecule became part of a cell that pumps with every heartbeat. Right now, while you listen, that atom is still there, pulled along in a rhythm that depends on air, food, gravity, and the steady warmth of the sun. A journey that began in the heart of a long-dead star now continues inside a person lying under a human-made roof. This is not a metaphor, it is the actual history of matter. Hydrogen from the early universe, helium and heavier elements from stars, dust and ice from collapsing clouds, rocks from planet-building collisions, water from comets and asteroids, chemistry from oceans and atmospheres, biology from evolution. Consciousness emerging from networks of living cells that learned to process information and anticipate the world. Once you see the chain clearly, Earth feels different. It is no longer just the backdrop for your personal life. It is a node in the cosmic web, a place where matter has arranged itself into oceans and continents and minds. The same rules that shaped galaxies and star clusters shaped this world. The difference is one of scale and complexity, not of kind. Think for a moment about how fragile this arrangement is. Our planet is wrapped in a thin layer of air. Its surface temperature sits in a narrow band where liquid water can exist. Its orbit is nearly circular. Its rotation axis tilts just enough to give seasons, but not enough to freeze or fry entire hemispheres. Its magnetic field and atmosphere help shield the surface from the harsher winds of space. None of that is guaranteed everywhere. Tilt a planet more, and its seasons swing wildly. Move it closer to its star, and its oceans may boil away. Strip its atmosphere, and the surface bakes by day and freezes by night. In that context, Earth is not a generic rock. It is a very specific configuration, the outcome of a long sequence of cosmic accidents and steady forces. Our species emerged late in this history. For most of Earth's lifetime, no one was here to look up and ask questions. For billions of years, life existed only as simple cells, then as more complex organisms in the sea. Only very recently did creatures appear who could walk on land, look at the sky, and wonder what the points of light were. Early humans did not have telescopes, detectors, or equations. They had eyes, stories, and fear and curiosity. They connected stars into patterns and told tales about them. The figures of hunters, animals, heroes, and ancestors drawn across the sky helped people remember seasons and directions. Those stories did not describe galaxies or expansion, but they met a real need. They gave the night meaning. In a way, modern science is a continuation of that same impulse. We still lie under the sky and invent explanations. The difference is that now we test those explanations against careful measurements. We build instruments that can see beyond visible light. We compare what we predict with what the universe actually does. Explanations that fail are discarded. Ones that survive many tests are kept and refined. Every fact you have heard in this story comes from that process. The idea that planets form in disks of gas and dust is supported by direct images of such disks and by the layout of many planetary systems. The claim that stars fuse hydrogen into helium comes from matching their spectra and lifetimes with detailed models. The confirmation that the universe is expanding and accelerating arises from multiple independent observations. We did not learn these things by copying one dramatic story from a single source. We assembled them by listening to the universe in many ways. Light, radio waves, X-rays, gravitational waves, particle showers. Each channel carries part of the evidence. When all those lines of evidence point in the same direction, we gain confidence that we are not just entertaining ourselves, we are uncovering how reality works. That gives your curiosity a different weight. When you wonder where your atoms came from, you are not asking a question that can only be answered with myth. You are asking something the universe has actually told us, piece by piece, through signals we can measure. You live at a time when those answers are available. You can know that you are made of matter forged in stars, arranged here by gravity and chemistry. Of course, knowing this does not solve daily problems. It does not pay bills or heal every hurt. Yet it changes the background against which those problems play out. It means that when you feel small, you can remember that you are also impossibly connected. The carbon in your chest, the calcium in your teeth, the iron in your blood, have all travelled across cosmic time to end up where they are. Imagine your life as a brief, bright pattern in that much longer flow, not a separate thing, dropped into the universe from outside, but a temporary arrangement of cosmic material. For a while, atoms that used to drift in hot plasma and cold dust are arranged into a body that can think and feel. They can look back along their own history and forward into their possible futures. Then they will move on into other forms. If that idea makes you feel insignificant, pause and flip it. Think about how unlikely it is for matter to organise into a nervous system that can understand stars and galaxies. Think about how tiny the window of time is when a universe full of burning suns and ripening planets exists at all. Within that narrow window, on one modest world, some of that matter has become aware. That is you. There is a kind of responsibility that comes with that awareness. You understand enough physics to know that your world is finite and vulnerable. You know that impacts, climate shifts, and your own technologies can change the conditions here. You know that the same curiosity that built telescopes also built tools that can harm. Science does not decide what you should do with that knowledge. It only makes clear that your choices matter. When you think about the future of Earth, it is tempting to imagine that cosmic forces will always dwarf human actions. Yet on the scale of your lifetime and your children's lifetimes, your own species is the dominant driver of change here. Star formation rates and dark energy do not decide how forests are cut or protected, or whether the air grows cleaner or dirtier. People do. That is another way your story loops from the vast to the personal. The same understanding that tells you about neutron stars and black holes also tells you how greenhouse gases trap heat, how pollution spreads, how ecosystems respond to stress. If you accept the cosmic story, you accept that knowledge is our main tool. We cannot bargain with gravity, but we can choose how we live under it. You can also choose how to live with this perspective emotionally. Some people feel overwhelmed by it, lost in the scale. Others feel comforted, as if personal worries shrink against the backdrop of 14 billion years. You may feel both at different times. The point is not to force one reaction. It is to let the facts be what they are and allow your response to grow honestly from them. Here is a simple exercise you can try. Maybe not tonight, but the next time you see a clear sky. Pick one bright star. Remember that its light left before this exact moment in your life existed. Think about how it formed from a collapsing cloud, how planets may circle it, unknown and unseen. Think about how in some distant future it will change or die, and how you are catching it in one brief phase. Then lower your gaze and look at something very ordinary near you. A tree, a building, a cup of water on a table. Know that every atom in that object shares the same general history as the atoms in your body and in that star. They all come from the same early universe, shaped by the same forces. The difference is in the paths they took and the patterns they now form. That is the heart of this entire journey. The universe is not elsewhere. It is not just out there beyond the atmosphere. It is also in here, in your hands, in your thoughts, in the devices you use to listen. When you learn how planets form, you are also learning how your planet formed. When you learn how stars die, you are learning how the elements in your blood were released into space. So tonight, when you eventually close your eyes, you can imagine yourself on a small raft in a vast ocean. The raft is Earth, floating in the dark between stars. The ocean is space-time, shaped by gravity and expansion. The breeze on your face is sunlight, a tiny fraction of the energy your local star pours out every second. The story you just heard is the chart you carry, showing how that ocean behaves. You do not have to solve the whole map. You do not have to hold every detail in your head. It is enough to remember a few simple truths. You are made of old stars. You live on a rare kind of world. Your species has learned to read the sky with a precision that would have seemed like magic to your ancestors. And right now, you are alive in the brief, bright epoch when the universe is full of stars and questions. If that thought follows you into sleep, let it do so gently. Let it fold around your everyday concerns without erasing them. Tomorrow you will wake up and deal with clock time again. Work, relationships, traffic, messages. Underneath all of that, the cosmic time you have just explored will still be flowing, slow and steady. Stars will keep burning. Galaxies will keep drifting. The atoms in your body will keep their quiet vigil. One day, far from now, those atoms will move on. They will rejoin the wider circulation of matter. The universe will forget your name, but it will not forget the patterns you helped create. The thoughts you shared, the kindness you offered, the knowledge you passed on, all become part of how this tiny corner of the cosmos developed. That is your part in the larger story. For now, You do not need to hold the entire universe in your mind. You only need to know that you belong to it, that the calm ceiling above you is the inner surface of a much larger reality, and that understanding even a small piece of that reality is one of the rarest experiences matter can have.